Okay, sorry, I have to rejoin again. Am I audible and the screen is visible to you all? Okay, thanks Aniruddha. What I was telling is we'll see a demonstration associated with the IP datagram. How actually the IP datagram propagates over the network, how the datagram is fragmented based on the maximum transfer unit or maximum transmit unit. The IP datagram we have here east network, west network. There are various components which are connected to the switch. The red laptop is connected to the switch at the rightmost of your screen, and a server is connected to the west network. The networking devices that are in between the east network and west network are the various network components or various local area networks supported by the interconnecting device, that is router. We have router A, B, C, D, E, F. The typical paths, by just viewing this particular diagram, we can say that the red laptop is connected to the west network with the support of in-between switches. One particular path will be from switch of red laptop to router F, then D, then A, and then switch of the west network. Another path may be switch, then router F, then router C, then router A, and again switch. The third path which is suitable, these are all, we are talking about the packet switching. Packet will be delivered to the destination based on the bandwidth that is supported by the communication media. If it's the optical fiber backbone, then the bandwidth that is supported will be very high. If it's the category 6 type of network, then the maximum length for the category 6 network will be 100 Mbps, or sorry, 100 meters. The devices can be connected in any of the topology. The in-between devices, the networking topology may be different type. Whenever the devices are of different type, the communication media is of different type, then the maximum transfer unit, maximum transmit unit are different. Just see this particular animation. An IP datagram travels over the different network, each of which may have a different MTU, which is the largest IP datagram that can be carried by the network. Now here, assume that east and west networks have an MTU of 1500 bytes. We have seen the various networks has various maximum transmit unit. In between has an MTU of 576 bytes. One particular network will have a maximum transmitting units 570 or maximum transfer units. It's one and the same. Now see here, red laptop, each is sending the packet towards the west network. Each packet will have a unique number. When a packet needs to be fragmented, this unique number is shared. Say ident 777. It's the identification number for that particular packet. And the packet size is 1300 bytes. Listen very carefully. Each packet has a unique number. Identification number is 777. The packet size is 1300 bytes. Since the size of the packet is less than the maximum transfer unit, it does not need to be fragmented. The packet maximum supporting MTU is 1500 bytes. Since the packet size is 1300 bytes, no fragmentation is required. Now from switch to, the packet is available at router F. The packet is 1300 bytes, but the MTU of the next network is 576 bytes. So the packet must be divided now, because you cannot propagate the packet larger than the maximum transfer unit. So the packet needs to be fragmented. The packet is 1300 bytes, MTU is 576 bytes. So the packet must be broken. See here, we have the identification for that particular packet 771. The status of the flag is now 1. This indicates that there are more fragments of the data. The offset is 0, which determines where fragment belongs to original path. It is the count of 8-byte units of the data. Now the packet size is 576 bytes. 1300 bytes minus 576 bytes. That will be the next. The identification number is 777, flag is set to 1, and the offset is 72. So the packet size is 576 bytes. Now here we have two different paths for that particular packet. One packet will have a offset of 144, so the packet size will be 148 bytes. The flag is set to 0. The identification number for that particular packet is 777. IP on the destination keeps a small buffer where fragments are put in order and reassembled. For this particular network, MTU is 1500 bytes. The network layer transfers those packets to the transport layer. The packets, see here, all the packets are first of all assembled here. Then the packets are put in the correct order and the original packet is then handed over to the transport layer. One of the fragments is lost now for the router C. So all the fragments in the destination buffer must be discarded and the entire packet is lost because only two fragments are received. Only two fragments are received. Fragmentation can be at the sender's end also, because in case of TCP and UDP, the network layer protocols and the transport layer protocols, UDP sends actually the datagrams. If the datagram is too big for the network, it is fragmented. Remember this very, very carefully. If the datagram is too big for the network, it is fragmented at the sender's end. The reassembly only happens at the destination end. The packet may avail any available path. The packet may available through any available path. Reassembly will be only happening at the destination node. Once again, we'll see this. An IP datagram travels over the different network, each of which may have a different maximum transmitting unit or maximum transfer unit, which is the largest IP datagram that can be carried out by the network. Assume that East and West network is having an MTU of 1500. East and West both have 1500. In between there is a MTU of 576 at the router F. The next network utilizes only 576. So the packet is divided into three different forms. Ident will be the same. First packet size will be 1300 bytes. The packet is 1300 bytes, but the MTU is 576. So 1300 bytes is divided into number of fragments. Here we are utilizing three different fragments. The packet size is now 576 byte. The flag is now set. The flag is set to, that means it indicates that there are more number of fragments. That is the indication to the destination end. So at the destination end, if this particular the packet is received and the flag, one of the component of that particular packet is set to 1, the receiver will know that there are more than one packet which is being defragmented in the network itself, and then at the receiver's end all those fragments must be received. Then only the defragmentation of the packets can be done at the destination end. Make your concept here very, very clear. The identification number remains the same. The offset provides us the packet size. From 1300 bytes, we have three different packets. The first will have an offset of 72. The second will have an offset of 144. So the packet size will be 148 bytes. That means the path for the packet from switch to router F to router C will be 148 bytes. That will be the packet size. And the remaining packets are again propagated through the path F, D and A. So one complete packet of 1300 bytes is divided into three different packets. One will be routed through F, D and A. Second packet will be routed which will have a size of 148. It can be any different size depending on the router C or router F, how the router F fragments that particular packet. But the packet cannot be transmitted above the maximum transmitting unit. So it's dividing into three different packets. One packet of 148 byte will have a path from RAID laptop to switch to F to router C to router A and to the destination, that is the west network. Then two different packets will have a path switch router F, router D, router A. All these three packets will be available in the buffer memory of west network. See here, three different packets. All these three different packets are kept in the buffer. They are put in the order. The identification number is checked and then only the packets are reassembled. So the reassembled packet size will be 1300 bytes and these 1300 bytes will be then handed over to the transport layer. That's how the datagram is fragmented, defragmented based on the maximum transfer capability of the networking devices. If the bandwidth is more than 1500 MTU for all the devices, then there is no necessity to fragment the data in between the network. But it's not at all always the truth. The bandwidth capability of every network is entirely different. That is not at all known also. So the in between devices always fragments the packet if the packet size is more than the maximum transfer unit MTU. Obviously, for the high-speed broadband optical fiber networks, the packet size is always very high. Maximum capability of a packet size that is defined is normally 65, around 65K. That is the maximum transfer unit. That is the packet per unit that can be communicated over the entire network. I hope the concept of fragmentation, defragmentation and assembly is quite clear to you. Look at this diagram. East network has the maximum transfer capability 1500. West network also can the 1500 bytes, but in between network, internet has the maximum transfer unit of 576 bytes. And that's why the packet is to be divided, the packet is to be fragmented, and then only the packet reaches the destination. Is the concept clear? Just put it in the chat box. Fragmentation, disassembly and reassembly. Is this concept clear to you? Just put it in the chat box. I think Snehal and Pooja seems to be attentive. Remaining all are not at all available or part of the network. The packet is still not reaching to them, it seems. This concept is quite important. This will tell us how actually the packet is propagated, how the packet is divided into number of fragments. Fragmentation happens due to the MTU capability of in-between devices. If MTU capability, nowadays optimum capability that is supported is normally 512 bytes and in the multiples of 2 raised to n. But if the device is not able to, now what happens if the size of the packet is not sufficient to the MTU, say only 100 bytes is to be transferred and the maximum transfer unit for the internet is 576 bytes. These 576 bytes, since the capability, since the size of the packet is less, that will be immediately delivered towards the destination. Normally, once the path for the datagram is set, the consecutive packets or the packets may be divided into the 3 different packets at router F itself, and the packet will propagate from red switch to F to D to A to switch and towards the west network. It's not always that it will always be propagated through C. If router C is not at all responsive, the router F may avail the path from router F to router E, then router B, then router A. Since the number of devices in between goes on increasing, the charge on the packet goes on increasing, the cost of the communication goes on increasing, and that's how we divide the cost. Now, how actually the path is decided? Suppose this particular network, suppose the specified network router, we will assign the weights. We'll assign the weights to the communication path. Now we have communication path router F to router C as 1, router C to router A as 2. So the cost of communication by assigning the weight for the path for the packet that is propagating from the switch of red laptop will be from F to C it's 1, from C to A it's 2. So the total weightage will be 3. If router F to router D has a weightage of 1, router D to router A has weightage of 1, then the weightage for packet to be propagated from red switch to west network switch will be only 1 plus 1, that is 2. So the weightage will be 2. Weightage can define the shortest path for the packet to travel from source to destination. And that's how routers are maintaining this particular shortest path. If router F to router E, there is no charge, that is the weightage assigned will be 0. From router E to router B, if it's again 1, and router B to router A, if it's 0, the lowest or the shortest path in terms of cost will be F to E, E to B, B to A. Since weightage will be only 1. There are different configurations. The weightage that is assigned to the communication path. The weightage may be the accounting weightage, that is the cost efficiency. The weightage may be in the form of distance. If we assign the weightage based on the distance, that is from F to E if it's 10 meter, from E to B if it's 10 meter, from B to A if it's 10 meter, then the weightage will be 10 plus 10 plus 10, that is 30 meters. If router F to router D is 5 meters and router D to router A is 5 meters, then the weightage associated with the distance will be only 10 meters. Similarly, if F to C weightage that is assigned is say 10 meters and C to A is 10 meters, then the shortest path will be F to D to A. Since weightage in terms of distance is the shortest path for the packet to be propagated from the sender's network to the destination network. And there are various algorithms which actually defines the shortest path, and all these routers are maintaining this particular shortest path in terms of cost, in terms of bandwidth, in terms of weightage. In terms of weightage, that will be the distance, and one of the algorithm is the distance vector routing. For propagating the packet from east network to the west network, if the distance vector routing is to be calculated, every router will maintain the distance of nearby routers so that that specific cost effective weightage can be assigned to the packet, and the packet will be delivered towards the destination end. This actually provides us the optimization that is required for the propagation of a packet from source network to the destination network. We are going to see the details associated, but at present, just for this particular diagram, you can recall that we are finding out the shortest path towards the destination end. The shortest path may not always be the physical distance. It may be associated with the maximum bandwidth that is supported. Say this particular FDA is a coaxial cable and FCA is a optical fiber path. Then the maximum transfer units will be very large for this particular path FCA, since bandwidth supported by the communication media connecting the routers is quite high, and that's why typically for the packets are always propagated where the bandwidth supported by the backbone communication media is quite high. Suppose F2E is a satellite network and the cost of communication is very high. So the cost of communication specifically for the coaxial cable is quite low. The coaxial cable is utilized, that means the distance towards destination is also very low. So the packet will be propagated from F to D to A based on the cost of communication, based on the bandwidth, based on these are the three important parameters with which we are actually finalizing the routing algorithms. We'll see the much more details about this. At present, just remember that the packets are defragmented based on the maximum transfer unit. For our network layer consideration, for our unit phi, this is sufficient. We'll go to the various router algorithms in the next unit, that is unit phi. I think I will take the questions. Any questions? Either you can put it in the chat box or unmute yourself and speak it. Are there any questions? You can ask any question. Sumit, Rutuja, Snehal, any question?
No, sir.
Aniruddha, Divesh, Komal,
No, sir.
any doubt, Divesh? One of the important concept at the network layer, delivery, forwarding and routing. The network layer actually provides us the configuration for the delivery. The network layer supervises the handling of the packets by the underlying physical networks. There are two different configurations associated with the delivery, the direct as well as the indirect delivery. The delivery of the packet to its final destination is done by using two different methods, the direct and indirect. In the direct delivery, the final destination of the packet is a host connected to the same physical network as the deliver. कोण कोण आवरून बसलं हो. The direct delivery occurs when the source and destination of the packets are located on the same physical network, or when the delivery between the last router and the destination host, that is, the two devices are in the same network. The sender can easily determine if the delivery is direct. It can extract the network address for the destination, of course, for the destination.
गाडीवर मागितली त्यांनी महाग होत्या त्याला सांगायच्या आधीच तो घेऊन नवीनच टाकी जर काही सगळ्यालाच नवीन टाकी देतील नवीन काय कर
Should we continue? The direct versus indirect delivery. Direct delivery is the delivery of the packet for the terminals in the same network, or the devices that are connected to the router and the internal device which may distribute the packet for all the terminals in the network. That is done by various software configurations, that is done by the utilization of the various types of firewalls. But at present, just remember that the sender can easily determine whether the delivery is to be done by a direct address or an indirect address, because it can extract the address of the destination or address of the destination where the packet is to be delivered by utilizing the IP address and the subnet mask. If the IP address and subnet mask, by utilizing it, the sender can calculate whether the destination is part of the same network or not, then the delivery is a direct one, because By utilizing the IP address and subnet mask, the terminal can identify whether the destination is in the same network or the IP address configuration is different. If it's in the same network, that is one particular terminal, say a local area network 192.168.0.1 and another network 192.168.0.250. Though the addresses are different, the addresses are in the same local area network. By utilizing the subnet mask which is configured for both source and destination, by just identifying, the source can identify whether this particular IP address is part of the same network or of the different network. If the address resolution is giving the information that the destination is part of the same network, then it's a direct delivery. If the destination host is not on the same network, the packet is delivered indirectly. That is, the packet hops from one network to another network to another network, till the destination path is found by the router, which is helping in hopping the packet from one network to another network. But that particular physical path of the destination must be also very, very, very clear. See here, direct delivery, host, network, another host is part of the same network. This particular network is getting connected to the rest of the internet with the help of the router. That will provide us the direct delivery configuration. The indirect and direct delivery. See, this particular source is part of one network. This destination is part of another network. The two networks are connected with the help of router. So the indirect delivery will be from host to first network to router. This router will check whether the destination is part of the network or not. If the destination is part of the network to which this router is connected, the packet will be delivered directly, or it will hop to another router. That is the indirect way of delivery. See here, the another concept that is used at the network layer is forwarding. Forwarding is actually, it's a means to place the packet in its route towards destination. The forwarding requires a host or a router to have a routing table. Make this very, very clear, the concept of routing table. The routing tables, see here, routing tables based on the route. Destination is host. The route is R1, R2 and host B. Destination is host B. In between we have router 1, router 2, host B is connected to router 2. The destination will always be found by using the routing table utilized by the routers R1 and R2. Specifically, see here, host A is connected to a network is connected to a router. In between router 1 and router 2, there is again a network, a common network. Then host B is connected to a network with which router 2 is connected. There will be two different configurations, the based on the route and based on next hop. So for the routing configuration, the route will be R1 to R2 to host B. It will be initially from host A to R1. Then from R2 to host B. R1 to R2, then R2 to host B. The routing table for R1 will define the next path or next hop of the packet, which is to be from the host A to host B. R1 routing table defines actually the entries, and this particular configuration is the forwarding of packet based on route or forwarding of the packet based on the next hop. We have seen the typical example associated with trace route. Trace route actually hops from one network to another network. Just try to utilize the trace route command, trace route from say your terminal to say intel.com. It will provide you the routing table configuration or the entries in the routing table based on the hopping from one IP address to another IP address. That IP address is the IP address that is being assigned to the routers in between the source and destination. Here you can get the clear idea. We have a server routing table for say host S based on the host specific methods. For destination A, the hop will be always the router 1. The routing table for host S based on the network specific method will be destination will be N2. All the terminals that are connected to N2 can be accessed or can be in the part of the network for the packet that is being transmitted from S. Routing table and hopping. Routing will be from destination A to B, A to S to N1, N1 to N2, then N2 to A. If S wants to communicate with A, that is S to N1, N1 to R1, R1 to N2, N2 to A. For the packet or for the hop based method, it will be jump from packet from N1 to N2. Then N2, it's the responsibility of N2 to distribute the packets to the specified destination A, B, C, D. So it's not at all always necessary to maintain the physical path of all the devices of network 2 at the network 1. So it's only the virtual address that is must be known. Virtual address, that is the IP address for N2, must be known so that the packet will be properly destined to the destination IP address N2. That's the host specific method of maintaining. If the number of devices goes on increasing, then it will be a destination and the next hop that will be part of the routing table. Here in this particular example, for host A, the routing table will be from N1 to N2. The default router may be connected to R2, then R2 to rest of the network, and R1 and network 2 are part of a common router that is connected. But if the path is not at all for the specified, then N2 to R1 will be the first hop. From R1 to N1 will be the second hop. And from N1 to R2 will find out the destination path for the packet. So for a classless type of network, the packet will be extracted, the destination address is extracted, search whether that destination address is available in the network allocation table, NAT table, the entire table is searched. Then next hop address and interface number is identified with the utilization of address resolution protocol for a local area network, and then the packet will be delivered. We need at least 4 columns in a routing table. Say, for this particular example, we have M0, M1, M2. We have one particular range of IP addresses connected to the router 1, which starts with the IP address 201.4.22.0. slash 24 indicates the number of hosts that are available for the router 1 having the range of IP address 201.4.22.02, the maximum number of hosts defined by the subnet mask for that particular network. These are four different networks having different range of IP addresses, which are connected to router 1. The meaning of this is that four different networks are connected to router 1. There are four different switches if we are utilizing the star type of topology. Each switch will define, one particular switch will define the range of, for this particular range of IP address, second will define for this particular range of IP address, third will define for this range of IP address, and all this will communicate with the external network with a router having the IP address range 180.70.65.200. So this particular IP address will be part of the network having the range 180.72.65. So one router, this router will have IP address 200. This router will have IP address 194. All the devices will have the specific range of IP address which are interfaced with the router's IP address. So this will be your propagation path decided by the IP address that is being assigned to R1 and IP address being assigned to R2, and then it will propagate to the external network. This particular external network will actually define the forwarding process, the entire forwarding process. This will be the routing table for router R1. 2625, that is actually the IP subnet mask. Subnet mask specifically will be, these are all the class B type of IP addresses. The class B type of IP addresses having the subnet mask 255.255.0.0. That will be the subnet mask for this particular network. These are the interfaces. M0, M1, M2, M3. These are the interfaces which actually provides the hopping for the packet. Again, similar type of configuration. This typical configuration is known as the address aggregation configuration. The routing in the classless addressing mode actually utilizes different type of principle. It's actually the mask that is being utilized. The mask, whenever it utilized, it's actually checks or matches the identified IP address with the IP address that's available in the table. This actually gave rise to the different configuration. The router 1 is having one particular hierarchical level, router 2 is having another hierarchical level, because it may happen that if the number of terminals here are quite large, number of hosts that are connected to router 1 are quite large, that is almost 256 devices, 256 switches are connected. To every switch there can be a maximum connectivity of 24, 32 or 64 host terminals. That goes on increasing, and it may happen that it may be a gigantic router table that may be created. In order to avoid that, we can define the hierarchy that is being associated with the router 1, router 2, so router 3, router 4. If router 4 is at higher hierarchy, all the addresses first of all must be available at router 4. Router 4 connectivity with router 3 is known. Router 3 connectivity to router 2, router 2 to router 1. This will be the propagation for the packet. This will be the propagation path, and based on that a suitable interface will be selected and hierarchical routing will be provided. This actually reduces the size of routing table because it's the router need not keep all the IP addresses, all the physical addresses of all the organization 1, 2, 3, 4. For all the 4 organizations, it's not at all necessary to maintain the IP to MAC configuration. For router 2, if it's at a higher hierarchy, it needs to have only the IP address and the MAC address that is assigned to router 1. For the incoming packet, for the destination packet, all these will have the public domain IP address of the R2. If it's R2 is the regional internet service provider. So internet service provider will actually define the different sub blocks. These sub blocks will have different IP address configuration. These IP address configurations may be all the internal IP addresses, but all these networks. That's why I have given you the example. Whenever you browse from any terminal in our entire campus, the public domain IP address for all the terminals will be a single IP address which is being assigned to either the firewall or the layer 3 switch. If firewall is absent, it will be IP address that is of the layer 3 switch that is assigned to as a public domain IP address to the layer 3. In our entire campus, we have cyber roam firewall. The cyber roam firewall is allocated one particular public domain IP address. Whatever may be the type of classless or classful type of IP addressing scheme that is used in the entire network, for all the terminals, only a single IP address will be assigned as a public domain IP address. And this public domain IP address, this particular firewall, this particular layer 3 switch will always maintain the entire IP and MAC configuration by the internal address resolution protocol, but externally it will only be connected to the router of an internet service provider. So your first hop will be from your router to the router of the service provider one. Then service provider hop will provide the next trace or the next hop of the address. And that's why nowadays, of course, the hierarchical IP addressing is also not at all suggested. It entirely depends on, see this particular configuration. See this hierarchical type of configuration. The total number of addresses, it's not at all required for this particular configuration. See, the total number are 16384, but it's not at all necessary. It will store only the hop addresses. These hop addresses, for this particular hop addresses, there are 4096 terminals. For this particular, there are 512 terminals. These 512 terminals are the terminals which are having a specific range of IP addresses, say 120.14.64.0 will be one range of 264.127. This will be the number of IP addresses. Here it will be 128. Then there will be another network. Then there will be another network. There will be fourth network. So such 4 different IP addresses will constitute 512. This network 512, this network 512. All these entries, it's not at all possible. So it will just maintain this particular configuration. This hop will maintain the IP addresses of 512 devices. This will maintain for 512. This will be another organization. This will be another organization. In such way, if the totals are 4096, then the destination for the specified terminal will be routed hierarchically from this particular router to this router, then the internal switch which is connecting the specified network. It's very, very necessary for you to identify how actually the hierarchical routing is identified by the internet service provider. Specifically, whenever you are part of a broadband network or a home broadband, there are not necessarily you will have always all the 512 devices which are assigned a public domain IP address. So, internet service provider assigns one particular public domain IP address to your router. This router is having two different configurations supported for the translation of the IP address to the MAC address. And that's how the router will propagate for your packet towards internet or from internet to the specified host terminal. The common fields that are available for the routing table: mask actually defines the starting address, defines actually the ending address, which can define whether your terminal is part of the internal network or an external network. Then the network address, then the next hop address, then the type of interface. Type of interface, normally for all the specified configurations, whenever we are utilizing the Ethernet configuration, then the Ethernet configuration can be defined by utilizing a MAC and IP translation configuration. So MAC will be connected to the IP. IP can be a dynamic type of IP, but the physical address will remain the same, and that particular physical address is nothing but the interface. Then the flags which will define whether the packet needs to be properly fragmented based on the maximum transfer unit, whether that particular packet is a data packet, whether that particular packet is a control packet, and that's defined. This actually provides you, see here, I have shown you this in the practicals. One of the command that can be utilized at the command prompt, if config. If config actually provides you the hardware address and the broadcast address and the mask that is utilized at the command prompt. Try this at your end. If config. Specifically, in case of Unix command prompt, you can utilize this if config. IP config is utilized for the Windows configuration. See here, configuration of a server. For the example that's given in the versions book 22.6, it's the default router which is actually defining the public domain IP address. Public domain IP address will have the range, the IP address in the range 153.18.0/22. That is the subnet mask of 255.255 dot something and something. So which will restrict the interface having the MAC address 00B0D0DF095D and the IP address in this configuration 153.18.17.11, because it's in the class B type of configuration. The first two 153.18 will remain the same, remaining all will be a variable, but that will be part of this particular network, and that's how the server is assigned the IP address. I think this much configuration, this for your unit 5, it's quite sufficient. Okay, we'll finish up this also. IP version 6 addresses. These are the configurations we have seen. For IP version 4, it's a 32-bit address, and for IP version 6, it's 128-bit address. The IP version 6 address is 128 bits long. This is the typical configuration. 128 bits. That means 16 bytes. That means 32 hex digits. So this will be the hex digit configuration colon notification. So it can be a suppose you want to assign a IP version 6 address. The IP version 6 address will have a typical configurations of say FDEC colon 192.168. There will be a double colon marking FDEC colon again colon, and it can be a 192.168.0.8 or 0 dot anything. That will be a one of the representation, that is the hexadecimal double colon notification including the IP version 4 configuration. Say this will be one of the configuration. If the number of devices are quite large, the gap is configured by utilizing double colon. See here, now the original address is FDEC colon 0074 colon 00. This is 128-bit address represented by the hexadecimal configuration, hexadecimal 16 16 16 16 16 16 16. This particular original configuration can be abbreviated. If it's all zeros, then it's abbreviated to 0. If there is 1 0, then it cannot be abbreviated. It cannot be abbreviated. If it's B0FF, it's taken as B0FF. So abbreviated address will be FDEC 0074 as 74. The leading zeros are truncated. All zeros are taken as only zeros, but the trailing zeros are not truncated. Remember this. Leading zeros are truncated, all zeros are taken as 0. So 0074 will be represented as FDEC colon 74. But it's again a hexadecimal address. That is 0074. So it will be 00000000 up to 16 times. Then representation of 40111 will be the representation for 7. Then 0100 will be representation for 4. That's how the IP version 6 addresses are abbreviated. See here, there are now more abbreviation can be done by utilizing the zeros as colons or double colon configuration. So FDC colon 74, double colon means the in between addresses are the zero addresses. Zero addresses provides us the abbreviated gap in between the hexadecimal addresses. So B0FF, there are two different gaps, so two colons. So this particular colon, if there are 3 zeros, then it's 2 colon representation. If there are 1 zeros, then it's a single colon representation. So it will be FDEC colon 74 double colon B0FF single colon 0 again single colon 0 0 single colon FF F0. Leading zeros are abbreviated, trailing zeros are not abbreviated. See this particular example. These are the typical configurations. I think we'll cover these IP version 6 addresses in the advanced networking. At present, just remember how actually we configure the IP version 6 addresses. It's a 28 bit. So starting is always a 11111111. These 8 bits. Then flag, 4 bits for flag. 0000 permanent, 0001 is the transient. The two type of addresses that can be assigned, permanent address and the transient addresses. Then the scope is divided into reserved, node local, link local, site local, organizational, global. 1111 for the scope, still reserved, not utilized in the IP addresses. And remaining 112 bits will define the group ID. In case of IP version 4, if you recall, host and network ID. The first was the network ID, and then last decides the host ID. Here 112 bits define actually the group ID for IP version 6 configuration. These are the typical IP addresses. In case of IP version 4, I have told you loopback address 127.0.0.1 is specifically reserved as a loopback address. As a loopback address. See here, IP version 4 address compatibility can be identified. See here, IP version 4 address. Here, IP version 4 32-bit address can be defined as the 00000, that is the starting 8 bits. All in between 88 bits will be zeros, so that a proper compatibility in IP version 4 and IP version 6 can be utilized, so that even if one of the terminal is IP version 4 assigned IP address terminal, it can communicate with IP version 6 configuration with the support of proper source and destination IP address schemes. So these are the link local, site local addresses. I think this much information is sufficient for our computer communication network, CCN. We'll see this distance vector routing in the coming lectures, the routing that is suitable for IP configuration. You can stop here indeed. Write your enrollment number as an attendance in the chat box. Write your attendance in the chat box.